We're going to take a look at a new integration technique that will allow us to find antiderivatives for functions that we were not able to do that before. In order to motivate this discussion, we're going to compare two different antiderivatives. First, we have the antiderivative of x e to the x squared dx, and we're going to compare that to the antiderivative of x e to the x dx. We can solve the first of these using u substitution. If we let u be x squared, then du, which is 2x dx, appears within that if we just divide out by 1/2. Notice, though, that if we try a similar substitution on the second antiderivative, it won't work because the derivative of x is just dx, and we have no way of getting rid of the x in front of e to the x. So substitution won't work for this antiderivative. It's not a known antiderivative, so we need a new rule. Notice, however, that it is the product of two functions, and that's going to be important to the way we approach solving this. We used the chain rule to help us figure out how to do u substitution. Now we're going to use the product rule to come up with a procedure called integration by parts. Recall that the product rule tells us that the derivative of the product of two functions is equal to the first function times the derivative of the second, plus the second function times the derivative of the first. So it follows that if we take the antiderivative of each side of that equation, the equation will still hold. But notice then that the antiderivative of the left side is just equal to the product of f times g. This gives us that f times g is going to be equal to the antiderivative of f times g prime dx plus the antiderivative of g times f prime dx. We can rearrange this a little bit to get us a form that's slightly more useful. Moving some terms around gives us our first look at what the integration by parts formula is. We see that the antiderivative of f times g prime dx is equal to f times g minus the antiderivative of g f prime dx. We'll do a few substitutions to rewrite this rule in its more traditional form. We're going to let u stand in for f of x, which means that du is going to be equal to f prime of x. We'll replace g prime of x with dv, which means that v is going to stand in for g of x. Once we make the substitutions, we see that we can write the rule as the antiderivative of u dv is equal to u times v minus the antiderivative of v du. At first glance, this may not appear to be particularly useful, given that we still have an antiderivative to figure out on the right-hand side. However, our goal here is to pick our two functions, u and v, so that u is a function that is easy to differentiate, and dv, the derivative of v, is a function that is easy to anti-differentiate. Let's go back to our original example and see how this works. That problem was the antiderivative of x e to the x dx. The x part of this is easy to differentiate, so we're going to let that be our u, and we'll see how that works out. When we set x equal to u, we can see then that du is the same as dx. That leaves e to the x dx as our remainder, and we can see that that is easy to anti-differentiate. So we'll set dv equal to e to the x dx, and we'll take an antiderivative to get that v is equal to e to the x. Now we'll plug in our component parts. We start off with x e to the x, which is u times v. We'll subtract from that the antiderivative of e to the x dx, which is v times du. That antiderivative is easy for us to solve, so we see that our answer is x e to the x minus e to the x plus some constant c. Let's try another example, this time involving a trig function. We're going to find the antiderivative of x cosine x dx. We'll let u be x again, because that's easy to differentiate. And we'll let dv be the remainder cosine x dx, because that's fairly easy to anti-differentiate. So we see that if u equals x, then du is dx. And if dv is cosine x, taking an antiderivative of that, we get that v is equal to sine x. Now we'll plug in the corresponding parts. So we get x sine x minus the antiderivative of sine x dx. Again, we've created an antiderivative that's simple for us to do. So we get x sine x plus cosine x plus c. Our next example is going to look similar to the last one, except we're going to see that we have to do a trick involving integrating twice. So we're finding the antiderivative of e to the x cosine x dx. We'll let u be e to the x, again, easy to differentiate, and we'll let dv be cosine x dx. So we see that du is equal to e to the x dx, and then anti-differentiating dv equals cosine x dx gives us that v is equal to sine x. When we plug into our formula, we'll get u times v is e to the x sine x, and the antiderivative of v du is sine x e to the x dx, which we'll rearrange as e to the x sine x dx, which looks an awful lot like the thing we started with. Before we give up, we'll try doing this one more time. So once again, we'll let u be e to the x. We'll let dv be the remainder of the function, so sine x dx. So we get u equals e to the x, and du is again e to the x dx. If dv is sine x dx, then v is going to be negative cosine of x. We'll plug it back into our formula again. So the first part stays the same. We have e to the x sine x. Then we're going to subtract off all of the new uv, which is negative cosine x e to the x, minus the antiderivative of v du, which is going to be negative cosine x e to the x dx, which we'll rearrange to put the e to the x in the front. Now, right now it looks like we've just gone in a circle. However, we're going to distribute our signs and notice something. So we get e to the x sine x plus e to the x cosine x minus the antiderivative of e to the x cosine x when we put those three negative signs together. So let's take a look back at where we started. We started off with the antiderivative of e to the x cosine x dx. Differentiating twice by parts, we got e to the x sine x plus e to the x cosine x minus e to the x cosine x dx. Let's move that last integral over to the left-hand side. That gives us 2 times the antiderivative of e to the x cosine x dx is now equal to e to the x times sine x plus cosine x, when we factor out the e to the x on the right-hand side. We can just divide both sides by 2 now, and we see that our original antiderivative, e to the x cosine x dx, is going to equal 1/2 e to the x times sine x plus cosine x plus our constant c. Our next example might not look like a typical integration by parts example in that it's not obviously a product to start off with. However, we don't up until this point have an antiderivative for ln x, so let's see what happens when we try to apply it. We'll let u be ln x, mostly because there isn't another choice, which leaves dx to equal dv. When we take the derivative of ln x, we know that that's equal to 1 over x dx. And if dv and dx are the same, that must tell us that v is equal to x. Plugging into our formula, we get u times v is x ln x minus the antiderivative of v du, which will be x times 1 over x dx, We can tidy up that integrand on the right-hand side. We get x ln x minus dx, which gives us as our final answer x ln x minus x plus c. We'll do something similar now to find the antiderivative of an inverse trig function. We're going to investigate the antiderivative of inverse tangent of x dx. We'll let u be inverse tangent of x, something whose derivative we know. We remember that the derivative of inverse tangent is going to be 1 over 1 plus x squared dx. And then we have dv equal to dx, which is once again going to give us that b is equal to x. We'll plug this into our formula. So we get x times the inverse tangent of x minus the antiderivative of v du, which is going to be x over 1 plus x squared dx. That antiderivative we're going to need to use substitution to solve. So we'll let u be the denominator, 1 plus x squared, because we can see that a multiple of its derivative appears in the numerator, and we get that 1/2 of du is equal to x dx. Making our substitution, we'll have x inverse tangent of x minus 1/2 the antiderivative of du over u. We know that that is the natural log of the absolute value of u, so we get x inverse tangent of x minus 1/2 the natural log of the absolute value of u. And our final answer is x inverse tangent of x minus 1/2 the natural log of 1 plus x squared when we back substitute, plus our constant c. For our final example, we'll do a definite integral using integration by parts. So let's evaluate the integral from 1 to e of x ln x dx. We're going to let u be ln x and x dx be dv. This is a little different than what we've done prior to this. We're not choosing the first thing as our u and the second thing as our dv. Instead, we're using u as ln x because its derivative is simpler, 1 over x dx. And then if we let dv be x dx, we know that v is going to be x squared over 2, which is much simpler than the antiderivative of ln x, which we looked at previously. So this becomes x squared over 2 times ln x, evaluated from 1 to e, and then we'll subtract the integral from 1 to e of x squared over 2 times 1 over x dx. Plugging in e gives us e squared over 2 ln e. Plugging in 1 and subtracting that gives us minus 1/2 ln 1. We'll pull the 1/2 out in front of our antiderivative, so now we have the integral from 1 to e of x dx when we simplify that. Ln e is 1, so we get e squared minus 1/2 x squared over 2 when we antidifferentiate. Now we'll plug 1 and e into all of that. This gives us e squared over 2 minus our second integral, which when we plug in e, we get e squared over 4. Plugging in 1 gives us minus 1/4. We'll give ourselves a common denominator to simplify this answer, so we get 2e squared over 4 minus e squared over 4 plus 1/4, which simplifies to e squared plus 1 over 4.